Speaking about symmetries might feel as something cosmetic and idealized, but they really do hide not only the laws of universe, also the possibility of us knowing them. Behind them, there is the regularity we observe in nature, and that regularity enables us to predict responses based on what we have already observed, and thus to do science. The general concept is pretty straightforward. The symmetry is something that you change and leaves everything exactly the same. It's a transformation that leaves your system invariant. But do we really know how many and which are the symmetries of the universe we live in?
Let us begin with the symmetries of our conventional space and time, where we sort of live. These will be transformations that are applied to every point of our space-time. That's why they are called global, as opposed to local symmetries, which are point-dependent transformations. So, first of all, it's easy to check that laws of nature are the same wherever we are in space, here, there, and in the moon. These are translations. This also works for time. Laws of nature are the same now, 10 seconds ago, 10 seconds in the future, or in 1,000 years. This is nicely and simply represented by the abelian group in R4, which has dimension 4. Nature is also invariant whatever direction we look at in space. This stands for spatial rotations, which are represented by the group SO3, meaning spatial orthogonal. This adds 3 more dimensions to our symmetries. But we also have that all non-accelerating frames of reference observe the same laws. This goes for Galilean relativity at first, and later for special relativity, where these speed transformations, called boosts, can be seen as rotations into the temporal dimension. Then we have 3 rotations plus 3 boosts that send us to the Lorentz group with dimension 6. Putting all together, we have 3 rotations plus 3 boosts plus 4 translations in space-time. For that, we will need the Poincare group, ISO31, where this I stands for inhomogeneous, since the Lorentz groups acts in a non-trivial way on translations. This is not a small creature, but with practice you can handle it. What I want to underline here is that all these objects, mathematically, are all of them Lie groups. But this is not all. To this set of symmetries, which are global, we have to add others, the local gauge symmetries. They inhabit an internal space of the fields, not in one we live in, but where the interaction lives, we could sort of say. The reason why they are called local is that the transformation is allowed to vary from point to point, giving thus rise to the elementary forces. Of course, they are different. These space-like realms are not something where you can just wander around in, but they happen to have a structure which is surprisingly similar to that of our everyday space-time. The reason is that both of them are described by Lie groups with their Lie algebras. For electromagnetism, we have U1, with dimension 1. For the electroweak sector, we have SU2 with dimension 3. For the strong force, we have SU3 with dimension 8. All of them together conform the symmetries of the standard model, and they add up to 12. If we put them together with the Poincare group, then we have 22, a space of total dimension 22.
These symmetry groups are already pretty complex, but the big deal is that when we seek to unify theories, we must go to more and more complex groups in order to embrace all the rest of the groups in a single group and a single theory.
The symmetries of the standard model together already conform a quite big monster, yet not very elegant, since it is made of the direct product of the three groups of local symmetries. If you want to handle the smallest simple group containing the standard model symmetries, then you must go to SU5 of dimension 24, perhaps more elegant, but also a lot bigger. If that is not enough, you are still leaving neutrino masses and other stuff behind. So you easily find that you have to go for SO10, which is the reference group for grand unification theories, with dimension 45. But also, gravity makes things harder if you want to have a beautiful structure for it all. So physicists escalate their theories to E6 with 78 dimensions. And it does not stop here. If you want to get to a small simple group, somehow embracing the local and global symmetries, this is SU5 times IS031, standard model and Poincare group, then be prepared for at least E8, even larger, with dimension 248. But that one is still a little fish if you compare it with what you expect for string theories. The gauge group is then SO32 or E8 times E8, both of them 496 dimensions.
If a string theory is true, we live in a universe which hides symmetries in 496 dimensions. If that number tells you nothing, you can think that developing only the E8 group, this is showing its full structure, if written on paper at readable size, could take up the island of Manhattan. I wouldn't want to provoke upon myself the rage of the creator of the universe by questioning his choice. But for me, that feels like he wanted to screw us over. What I'd like to emphasize about all these symmetries is that they all belong to the same kind of skeleton, the Lie groups. And that make them some way linked to the concepts of vector space, differential equations, and more generally to the idea of continuity that Newton established. And that, of course, it has worked very well and has a lot of accomplishment. But it seems that keeping pulling on that idea of symmetry is driving us to more and more complex things and to some kind of mathematical phantasmagoria.
But I have left behind three very simple symmetries, which also have nothing to do with Lie groups. They are not continuous, they are discrete, but they do, at least in principle, seem clearly related to spacetime. They are temporal inversion, T, running time backwards, parity, P, inversion of spatial coordinates, and charge conjugation, C, which is switching positive and negative charges. This last one, charge conjugation, may seem unrelated to spacetime, but Since in quantum field theories, an antiparticle is equivalent to the particle but traveling backwards in time and in the opposite direction, it necessarily becomes equivalent to apply Pt jointly. These three symmetries, therefore, work as a bundle, and we know something particular about them. CPT and their combination of two are not conserved in some rate processes. Therefore, they are not perfect symmetries, or they are broken. But CPT, the combination of the three, is fully conserved as far as we know. Going back to the concept of overcoming space-time. Well, it couldn't be coherent to believe that the symmetries of space and time as we know them are fundamental if we don't think space-time is. But I wouldn't think either that gauge symmetries should be considered fundamental once we remove space and time, since their nature is spatial and they are local in space-time. They are indeed built on the real numbers. So some way they have that meaning. I'd say all then should be emergent. I don't know how all these symmetries could be reconstructed once we move to a out of space and time structure. But I think that the other discrete symmetries, Cp and T, can have a natural translation to that kind of a structure. For that, let's see a node of the network.
In my last video, I showed how collision events, if decoupled from its space-time bounds, could be seen as four-legged nodes. Let us isolate one of these nodes. The four legs of a node are not a priori identical, so we label them with numbers. You can nonetheless make permutations of the legs. We could do that vertically, horizontally, or diagonally, and we could imply the four legs on only two. At first, this is just a node, detached from any spatial concept. But if we establish a preferred direction as the flow of time, let us say it flows from bottom to top, we can interpret 3 and 4 as past and 1 and 2 as future. So, permuting then is T, time reversal. If we now permute 3 for 4 and 1 for 2, we are changing what comes and leaves from one side, this is the in and out legs, for what comes and leaves from the other side. This leaves what was inward as inward and what was outward as outward. This is like switching the colliding things and can be intuitively interpreted as changing left and right, or the mirror image of the node, or P parity. After this, we can conclude that C, however we describe it, should be the remaining permutation. Now check that if you go through with this framework, applying subsequently E, B, and C gets your node back to its initial configuration.
If we understand that the legs of this diagram are assigned a value, then if T, time reversal, must be preserved, the inward legs and the outward legs must sum the same value. Also, if P must be conserved, we know that the right side and the left side must sum the same value. If P and T must both be conserved, then 1 must be equal to 4 and 2 must be equal to 3. So goes on if we include C-Charles conjugation. If C, P, and T must be preserved separately, then we have that all legs must have the same value. But CPT as a single transformation has no particular requirements. And this is a clue, because we know that CP and T are not conserved, truly conserved, in our physics. So it makes sense to leave the values of the legs free and try to find out a mechanism that keeps them balanced, but not always. All right, what I've wanted to highlight here is that although research into laws of nature from the perspective of symmetries applied to spaces in the usual sense has been extremely fruitful, now it is ending in an escalation of complexity which I doubt it can lead to a really promising theory. However, moving to a vision without linear spaces and with an abstract network can take you back to a simple starting point from which symmetries could be emergent. Considering also that symmetries are, as physicists say, broken, we could see in those cracks a door to a more general rule.